photocopied the rubric with the feedback.
Oh,
It's been a horrid week. Cat's in the hospital and they've had her all weekend and they don't know what's wrong. They said, but she seems to be doing better, you can come pick her up. I'm like, oh good, okay, what was wrong? Well, we don't know. So, it's been a little bit okay. All right, so, respiratory system. This is not the correct PowerPoint, but I can't find, it's just going to be one of those weeks, obviously. I cannot find the correct PowerPoint. So as with the muscles and with the cardiovascular system, there's quite a lot of anatomy going on in order to follow what's happening when we exercise, all right? So if you're a little bit rusty on that anatomy, please make sure that you go back and review that information, because I'm only going to be able to go over it very quickly, all right? So for us, when we're looking at exercise, the key is what is going on down at the alveoli, all right? So you breathe in, down the bronchioles, into the lungs, and the lungs are very soft tissue, and they're made up of millions of these little balls that group together in sacs, all right? So when we're talking, most of what we're going to be looking at is going on at this level. Okay? All right, so the kind of big role that the respiratory system plays is as an interface for the exchange of gases between the air in the atmosphere and the blood. All right? And almost all of that exchange of gas occurs at the level of the alveoli. A tiny little bit occurs in the bronchioles as the air is moving through, but like 99% is going through the bronchioles, so that's where we're going to concentrate. All right? Before that exchange of gas can occur, in order to protect the very delicate membrane of the alveoli, the air is humidified as it passes through the nose and down through the bronchioles. That helps to prevent the membranes from drying out. And that's especially important when you live in a climate like we do, where humidity is very low and or it's very cold, because cold air doesn't hold on to water vapor as well as warm air, and so when it's cold, the humidity is even lower. All right? It warms the air up, which helps to maintain body temperature, means you haven't got freezing cold air coming into the lungs, which the body then has to heat up. Right? And hopefully it's filtering airborne particles. Clearly, with the amount of allergies we all suffer here, there's something that is getting through that filter in this area of the country. But most of the particles that are missed get engulfed by macrophages as they move through the system. So there's a lot going on other than just breathing in and out, but the gas exchange is the key. All right? So the alveoli, hopefully, oh yes, I don't need to do all that. The alveoli is like a little balloon, a little sac, right? And it's surrounded by capillaries. So there's lots of interface, lots of available membrane for exchange of gases between the blood in the capillaries and the air that's made it to the alveoli. All right? So when we breathe in, we're going to move oxygen out of the lungs into the bloodstream. When we breathe out, we're moving carbon dioxide that is a byproduct of aerobic metabolism out of the bloodstream into the air that we breathe out. Right? So because of their structure, and they estimate that we have somewhere around 300 million of these little alveoli sacs. They provide this huge surface area for this gas exchange to take place. And they reckon that if you opened all the alveoli up and laid them out flat, that your lungs would cover a tennis court. Right? So it's kind of like this, it's a similar reason that we see for all the folds in the brain. If you look at a brain, it has all these folds of tissue. That's to allow lots of surface area for exchange of nutrients. So it's a similar idea. If the lungs were just one solid object, we'd have very little surface area to move these gases backwards and forwards. Right? So the fact that they've evolved into these little circular structures just immensely increases the surface area that's available. Okay? And they term the kind of the structure of the membrane of the cell with the membrane of the capillary wall the respiratory membrane. So we've got two cell membranes, one on each side of the diffusion, and that's where oxygen and carbon dioxide pass in and out. So it looks like this. And I'm going to turn these lights off because we can't see the little piece. Okay, so let's start here. We've got somewhere around 300 million of these, all right, that make up the lung tissue, okay? And the alveoli is surrounded by this capillary netting, okay? So if we take a cut through, a horizontal cut through, you can see that literally the whole outside of the alveolus has blood vessels wrapped around it. So when we look here, this is the capillary with a red blood cell, and this is the inside of the lung, inside the alveolus. And so here is what we term the respiratory membrane. All right? So the respiratory membrane consists of the membrane for the capillary and the membrane for the alveolus. Right? I don't want the fuel sack. Don't worry about that. There we go. Let's see what we need. So this is so fascinating to me because it's not at all how I think about breathing. All right, we are able to breathe because we are able to change the pressure within the thoracic cavity. Right? So if I increase the volume of the thoracic cavity, inside the thoracic cavity. Then I increase lung volume. I decrease intrapulmonary pressure, and air rushes into the lungs. So before spring break, way, way back in the distant past, right, we talked about gases and fluids moving from where to where? Anybody remember? Right, they always move from an area of high pressure or concentration to an area of low pressure or concentration. All right? So, if you consider the first part of this information, all right, if my lungs, if I'm inspiring and air is coming into my lungs, right, so let's have the atmosphere and my lungs. So if air is moving that way, right, I'm breathing in, then my lungs have to be a lower pressure, that's the wrong way around. Lungs have to be a lower pressure than the atmosphere, right? Because it goes from high to low. Bless you. Does that make sense? All right. So we change the volume of the lungs, we change the pressure, and that allows air to move from high in the atmosphere to low in the lungs. Right? So in effect, we don't exactly breathe in the way that I consider I breathe in. We just change the pressure and the air gets sucked in, really, right? When we breathe out, then, we have the reverse. We decrease the lung volume, we increase the pressure in the lungs, and now it causes the air to rush out of the lungs. So we have the air moving in that direction. I'm breathing, oops, that's not work. Breathing out, right? So I have to have high here, low here. Right? So what's fascinating about this is that lung tissue is not contractile. Right? It can't move. So the lungs are not doing this, right? What's doing this is all the other mechanisms, that inspiratory muscles, the diaphragmatic muscles that move your chest, and your diaphragm moves up and down as you breathe. All right, so your diaphragm, if you want to go look at George after class, your diaphragm is the muscle that is like a big fat rainbow that sits under your rib cage above your stomach, right? So when we breathe in, when we're inspiring, right, the diaphragm contracts and flattens, and that puts pressure changes into motion. Right? And the muscles that elevate the ribs, right, increase the volume, and so the pressure drops down. And so air can go in. When we breathe out, we don't really have to do anything because the muscles just go back to their resting state, and that causes the pressures to change and the air to go out. Right? So most of the work by the diaphragm and the intercostal muscles that are involved in breathing occurs on the breathe in, not on the breathe out, typically. Okay? Right? So we change the pressure gradient. In this case, the pressure gradient is to do with gas, not blood, liquid, like it was when we looked at the cardiovascular system. But the rule is the same. The law of physics doesn't change. Right? There we go. Right? So here, the diaphragm contracts and flattens, the intercostals contract and spread the ribs wider. That increases the volume, decreases the pressure, air rushes in. The diaphragm relaxes, the intercostals relax, decreases the volume, increases the pressure, air runs out. So I think, to me, whenever we get to this chapter, I just find this so fun, because I consider that I breathe in a, like my lungs, or that I do the work, and really we don't. It just is a pressure change. Right? It just happens. Don't think we want that much info. We do want this one. About lumping these two chapters together is that what occurs in the respiratory system is basically exactly the same as what occurs in the previous chapter, except instead of blood flow, we have airflow. Right? But the rules and the equations are exactly the same. So you don't have to learn two separate sets of information here. All right? So airflow is the change in pressure over the resistance to the flow. Just like blood flow was the change in pressure over the resistance to the blood flow. Right? So airflow can be increased either by increasing the pressure difference or decreasing the resistance, right? Simple math. So changing the pressure difference is a bit of a misnomer. That's more complicated, right? Decreasing the resistance to airflow, the same as we do with blood flow, we can increase the diameter of the airway. Right? So when we're at rest, changing the resistance to airflow is mostly done by increasing the diameter of the bronchioles and how I'm getting air into the lungs. When we exercise, that bronchodilation is increased even further due to sympathetic stimulation and norepinephrine. Right? So we see even less resistance to breathing when we exercise, right? Now, you might not have noticed, or maybe you have, but when you go for a run or a bike ride, right, if you're working quite hard, after a little while, your brain will automatically switch you from breathing through your nose to breathing through your mouth. Right? So you go out for a run at the trail, and you have allergies, because we all do, right? And you're like, okay, I'm going to breathe through my nose so that my nose is filtering these particles and whatever, right? So you start off your jog breathing through your nose, you're doing a good job, and after about 5 minutes, you might find, hey, wait, and now I'm breathing through my mouth, and I didn't even think about it, it just happened. Because when you breathe through your mouth, because of the size of the airway versus the size of the nose, you get about 20 times more air into your lungs when you breathe through your mouth. So from your brain's point of view, it wants the most amount of oxygen possible to get into the bloodstream and get to the muscles for making ATP. It doesn't care that you have allergies and that breathing through your mouth makes your allergies worse, right? It's just trying to benefit the exercise pattern the best it can, okay? So what happens then when you work with someone who is asthmatic or is recovering from a really bad chest infection or bronchitis or pneumonia or something like that, is that these airways become constricted, right? And that constriction increases the resistance to airflow, and so their oxygen stats go down because they're not getting enough air into the lungs to transfer oxygen out to the bloodstream, right? And that's why asthmatics might have problems doing aerobic type work, right? So they may be advised by their doctor not to do a lot of aerobic work, but to do anaerobic work, okay? Be careful with the anaerobic work, because remember our EPOC idea, right? You could say, oh, well, I can do HIIT with them because HIIT is anaerobic, but remember that there's a payback after the... I still have to bring my temperature back down. I still have to get rid of lactate. I still have to move oxygen back into the muscle cell onto the myoglobin. All right, so because the exercise session is anaerobic, doesn't mean that there's not an aerobic recovery that they might struggle with, right? So you may have to start with lower intensities for someone who is asthmatic, even if you're doing anaerobic work. Possibly, right? Depends what meds they're on, how well they manage their asthma with their puffer, and things like that, right? Okay, so pulmonary ventilation then, we're looking at the amount of air moved in and out of the lungs over the course of a time period. So let's say a minute. That should sound very familiar, because that then is the same as Q, right? It's the respiratory equivalent. Pulmonary ventilation is the respiratory equivalent of Q. How much blood is moved out of the heart in a minute, right? Remember that Q equals stroke volume times heart rate. Okay. So tidal volume is the amount of air moved per breath. What's that the same as? What's it equivalent to in the cardiovascular system? What is how much air is moved per breath? How much blood is pumped per beat? How much air is moved per breath? Okay. So if we get that set up in the previous chapter, this is exactly the same. We just replace these terms with different terms. So tidal volume, the amount of air moved per breath. The volume of air moved per minute then is VE, right? Volume of air expired, Q, equals VT, stroke volume, times frequency. How many times per minute do I breathe? Heart rate. Okay. So it's going to be higher in someone who is trained, right? They're able to take a larger breath. They might be able to breathe more frequently per minute because their intercostal muscles and their diaphragm are stronger. Okay? So when I'm looking at a sedentary person, VE could go from about 8 liters per minute and at exercise about 113 liters per minute. So at rest, the trained person probably doesn't need a lot more oxygen than the untrained person, so somewhere around 8. But when you look at what they're able to do when they're exercising, the difference is very large. Can be up to 183 liters per minute versus 113 for someone who's sedentary. So that's heaps more oxygen they're able to move through the system. More oxygen means more ATP. More ATP means more frequent and stronger muscle contractions. Ergo, better athlete. Right? Now, the ceiling on your VE is a combination of your genetics and your training program. All right? So it's not like you can take someone who's got poor genetics and has a very small VE and turn them into a world-class endurance athlete, right? Genetics is always underpinning everything that goes on when we're looking at this information. Okay?
And the unit for liters, you said?
Liters per minute.
Per minute. Liters.
All right? So I can, let's get rid of all that rubbish. We can measure someone's lung capacity using a spirometer. So that's a lab test, although they are now creating spirometers that are small little computer boxes that you can wear on a chest strap, and have a small little mouthpiece in rather than a great big. Those of you that have done the VO2 max test know what that thing is. Really, really uncomfortable, very big thing. So we're at a point now where equipment-wise we can start to look at lung capacities and pressure changes and volumes in real-world situations for events where a little chest monitor would not get in the way. I mean, I can't do it for a gymnast or a diver, right? But I can do it for a long-distance runner or a biker or a sprinter, right? So we're starting to get some more real-world application of this information rather than just, because the problem with a lab is everything's consistent, right? And so it doesn't transfer directly to what we experience when we're actually playing our game or taking part in our event. When we look at the changes in breathing when we start to exercise, generally, right, it's accepted that what we do first is we start to breathe more deeply. So when I begin to go for my power walk, the first thing I do is go, right? And then, if that is not providing enough oxygen for the level of work that I'm doing, I'll start to breathe faster. Okay? So, the changes that occur are all to do with delivering oxygen to the working muscle. Once I'm delivering the amount of oxygen to create the ATP I need for the workload, everything that's steady state, breathing enters a steady state, right? Once I'm breathing at a depth or a rate that is providing what I need, it's going to stay like that unless I up the workload. So if I hit a hill, or I start to go faster, I change from a walk to a run, then my breathing will change until it's calibrated again. Okay. No, okay, so the diffusion of the gases is key. All right, so what do we have working in our favor to help us move that oxygen from the lungs into the bloodstream? So we've already mentioned the fact that we have a very large surface area, right? And we've got a respiratory membrane that is one cell on each side. So the alveoli membrane is one cell, the capillary membrane is only one cell. So it's very, very, very thin, and the distance that the oxygen has to move is minimal. Right? And then we come back to our partial pressure, our high-low, right? My partial pressure in the lungs is higher than in the bloodstream. So partial pressure of oxygen in the lungs is higher than the partial pressure of oxygen in the bloodstream, and so oxygen can diffuse across the membrane. We have laws that govern that. I'm not too fussed if the laws help. Good. Right. If not, ignore them. Let's look at the diagram. All right, so partial pressure pressure of oxygen in the atmosphere is 159.1 millimeters of mercury. So 159. Okay? The partial pressure of oxygen in the alveoli, in the lungs, is around 105 millimeters of mercury. So we have a pressure gradient that also aids with the fact that we're changing thoracic volume. Okay. Then this is basically the same diagram that we had previously. All right? What the blood that is leaving the right ventricle and coming to the lungs is quite low in oxygen. The number in the diagram is 40. It's going to depend on the individual, on whether they're exercising at that point or whether they're resting at that point, how trained they are, do they train at altitude, right? How much hemoglobin do they have? Would all change that number, all right? But for the sake of the example, partial pressure of oxygen coming to the lungs from the right ventricle is 40. Remember that it's 105 in the lungs. So that's a 65 millimeter mercury pressure gradient. So it's very easy for oxygen to diffuse across that tiny, tiny membrane into the bloodstream. Right? Think about my car on the hill, right? Really, really steep gradient, 65. Okay? So, now we've got 100. So the blood that is leaving is 100 versus the blood coming in, which was 40. 100 comes round to the left atrium, into the left ventricle, pumped out of the left ventricle. Remember, the left ventricle is the one that's doing more work. It's got to pump the blood all the way around the body. So out of the left ventricle, down to AN working tissue. So we're going to assume that this working tissue is muscle. Okay? The muscle needs oxygen. So oxygen will diffuse from the bloodstream into the muscle tissue. It's going to get across to the mitochondria, which is where system 3 is making ATP. Right? And we see 40. Remember our AVO2 difference? Is our AVO2 difference? 100 coming in, 40 coming out. That means 60 millimeters of mercury, pressure-wise, worth of oxygen passed across the membrane into the muscle tissue. Okay? Back to the heart, and it all starts again. Right? So we've got a steep gradient that drives the diffusion of oxygen from the bloodstream into the muscle tissue. Right. Now, when we're looking at our carbon dioxide in our muscle tissue, if I'm working aerobically, I'm creating carbon dioxide. Carbon dioxide is a nothing product. I can't do anything with it as a human. It's got to be out in the atmosphere for the plants to use. Right? So, my pressure gradients then, if I'm going to move carbon dioxide from the muscle tissue into the bloodstream, then my pressure gradient has to be high in the muscle tissue, low in the bloodstream. Right? That way I can diffuse carbon dioxide into the blood, gets carried around, comes to the lungs, and the partial pressure in the lungs is low, and so carbon dioxide can diffuse out of the bloodstream into the lungs, and we breathe it out. Okay? That's why we do not want to demolish all the rainforests in Brazil and everywhere. Because we breathe it out, they breathe it in, they breathe out oxygen, we breathe it in, we breathe out. If we don't have them breathing out oxygen, sooner or later, we won't be here. Not in our lifetime, but, okay? Okay? Eyes are rolling. All right, so I'm going to finish up the respiratory system on Wednesday. The nice thing about the respiratory system is there are very, very few adaptations. So once we understand how it works, not a lot change. It changes as we exercise, but it doesn't adapt over time. So there's kind of a chunk of stuff we don't have to do in this chapter, all right?